Okay, right. I'm going to work a couple of the practice problems set, and I'm going to do problem two first. By the way, I will um, post the answers to these. Uh, Maybe not this weekend because I may be out quite a bit, but no later than early next week. I'm going to post the answers. And again, you're not required to do any of the practice problems. They are going to be pretty good preparation for what you're going to see on the exam, so I recommend it. And problem number two is a problem in human genetics. There's a group of people, religious denomination founded in Germany in 1708, called the Old German Baptist Brethren, informally known as the Dunkers, because, well, they dunk people in their rite of baptism, as you know, Baptists do today. And a number of Germans, many of them belonging to non-mainstream Christian groups, emigrated from Germany to Pennsylvania. This includes the Moravians and the Mennonites and the Amish. I know you know about the Amish, the Schwenkfelders, and a number of others, and set up colonies in Pennsylvania. And as of 1950, when this work was done, there were roughly 3,500 Dunkers in the United States. Now, if you know the Amish, you know that they're pretty strict about lifestyle regulations, right? They don't wear colors. They don't adopt many aspects of technology. The Dunkers are not as strict as the Amish, but the Dunkers usually marry within their community. They don't go out of their way to attract converts. I mean, I guess it can happen, but it's not common at all. And Dunkers who marry non-Dunkers often end up leaving the community. So the Dunkers are an example of what's called a religious isolate, a population that has not really assimilated with the American mainstream, ultimately for reasons having to do with their religious beliefs. So in 1950, a geneticist named Bentley Glass looked at a population of over 200 Dunkers in southern Pennsylvania. And Glass looked at a blood group called MN. Since it can be hard for people to hear the distinction between M and N, I'm going to go ahead and use the NATO phonetic alphabet and say this is the Mike November blood group. And this is not one that is normally of much clinical significance, except in things like organ transplanting. But most of you probably don't know your Mike November blood group and may never need to know. And for just about every medical purpose, it really doesn't matter what it is. You know, you're not at greater risk of anything if you have one or the other of the Mike November blood groups. It so happens that this blood type is controlled by a single gene with two alleles, and the alleles are called Mike or November. If you're homozygous for the Mike allele, you have type Mike blood. If you're homozygous for the November allele, you have type November blood. And if you're heterozygous, you have blood type Mike November. You are heterozygous and you have the Mike November blood group. And as I've said, this has very little clinical significance as far as I'm aware. I'm not saying that there's never any, but most of the time it makes no real medical difference for most people. That's important, by the way, because it establishes, well, let me get to that later. Okay, right now, part A, Glass found 102 Dunkers that had type Mike blood and 96 with type Mike November and 31 with type November blood. Okay, I'm going to go to the whiteboard right now. Okay, can everybody see the whiteboard?
Yes.
Okay, great. All right, so we have, what is it, 102 dunkers who have blood type Mike, and that means that they have the genotype that we can write MM. All right, can everyone see that adequately? Do I need to try to make this larger?
I can see it pretty well.
Okay, I'm looking around at seeing if there's ways I can enlarge the text. But yeah, we may be kind of stuck with that. There's probably a way that I'm just not smart enough to find. Right. So we have 102 dunkers that have type Mike blood. And we have, dang it, hang on. (96) that are heterozygous, and 31 with type N. So that is 96 with the Mike November genotype and 31 with the November genotype. There, I'll move that so it lines up. Okay, so that's a total of 229 people, right? That's the sum of these three numbers. All right. And that means that the total number of alleles that are floating around in the population is double that, because everybody has 2 alleles. So that's 558 alleles, right? 229 people, 2 alleles per person. That's 558. Okay. How many alleles are Mike alleles? Well, the number of Mike alleles is 102 people who have 2 Mike alleles each, plus another 96 people who have 1 Mike allele each. So that's 102 times 2, which is 204, plus 96 times 1, which is 96, and 204 plus 96 equals 300 exactly. So of these 558 alleles, 300 of them are Mike alleles. Now the November alleles, the easy way is that it's just 558 minus 300, which should be 258. But if you want to do it the long way, is that right? Yes. You should have 31 people who have 2 of each allele, which is 62. And then add another, I did this wrong. This is not 558. That's 458 alleles. Hang on. Okay, so we have 229 people, 458 alleles, and the number of N alleles is 31 times 2 plus 96 times 1 again, right? 31 people have 2 November alleles, and 96 of them have 1 November allele, and that is equal to 62 plus 96, which is equal to 158. Okay. All right. So the frequency of our alleles, this is easy. So the frequency of the Mike allele is just 300 divided by 458. 300 divided by 458 is going to be approximately 2/3. If we want to get it a little bit more, 300 divided by 458 is equal to 0.655. Frequency of the November allele, the long way around is to calculate it as 158 divided by 458. And if I plug that into my calculator, I get 158 divided by 458. And that is equal to 0.345. Okay, quick check. Those two should add up to 1, and in fact they do. So there we have the first part of the problem. We have a population. We know their genotypes. It's easy to calculate the number of alleles. All you have to do now is count how many alleles are Mike and how many are November, and you can work out the allele frequencies. And for our purposes, we can call, hang on, that first frequency, 0.655, we can call it P. And that next frequency, 0.345, we can call it Q. And this is something you can do just as a quick check to make sure you did the math right. P plus Q, by definition, have to equal 1. Okay, you with me so far? All right, I'll take that as a yes. Here's our problem again. What we have to do now is calculate the expected numbers of people who would have each blood type if the population were in Hardy-Weinberg equilibrium. If the figures don't match what we observe, we need to try to figure out why that might be the case. Okay. So if the population is in Hardy-Weinberg, let's go back to the whiteboard. All right, let me see here. If we're in Hardy-Weinberg, then the frequency of Mike individuals is going to be the frequency of the Mike allele squared. The frequency of heterozygotes is going to be 2pq. And the frequency of the other homozygote, November, is going to be the square of that allele frequency. It's going to be q squared. Okay, so if we are in fact in Hardy-Weinberg equilibrium, then the frequency of Mike individual should be 0.655 squared, which is equal to, hang on, 0.655, which is equal to 0.429. Okay, for some reason I can't get these boxes to expand. Okay, maybe I can. There we go. There's a bigger text box. Okay, right. All right. If we're in Hardy-Weinberg, then the frequency of heterozygotes is going to be 2 times 0.655 times 0.345, and that's 0.452. Okay, if you're working along, you can check me on this, make sure I didn't mess anything up. And then if we're in Hardy-Weinberg, then the frequency of November homozygotes is going to be 0.345 times 0.345. All right, it's going to be 0.345 squared. Which is 0.345 times 0.345 is 0.119. All right. If we are in fact in Hardy-Weinberg, that's what we ought to see. Now, do we? Well, let me erase some of this. Whoops, did not want to erase all of that. Okay, dang it. All right, I erased more than I had intended. So let me type this over. If we are in, let me do this another way. If the populations in Hardy-Weinberg, our expected frequency of Mike individuals is 0.429. Our expected frequency of heterozygotes, Mike November, is 0.452. And our expected frequency of November individuals is 0.119. And I see I've written that twice, so I'm going to get rid of that. All right, what's our observed? Our observed frequency of Mike individuals, right, is, let me go back to the original problem. Our expected frequency of Mike individuals is 102 out of 229. Dang it. Our observed frequency of Mike individuals is 102 out of 229, which is equal to, hang on. 102 divided by 229, which is 0.445. Now it's doing it again. Okay, our observed frequency of heterozygotes is 96 divided by 229. And 96 divided by 229 is 0.419. And our observed frequency of November individuals is, let me see, that's 31. 31 divided by 229, which happens to be 31 divided by 229 should be equal to 0.135. Okay, I usually don't require you folks to do a chi-square test, although maybe I should, but that's your answer right there. The observed frequencies of the genotypes are these. 44.5% of the population is genotype Mike. About 42% of the population is heterozygous, Mike November. And about 13.5% of the population is homozygous for the November allele, has the November genotype. That's our observed. Here's our expected. This is what we would expect if the population is in Hardy-Weinberg equilibrium. Now, what we could do at this stage is plug this into a chi-square test and see if the difference is significant. I think we've done that before, and it turns out that it's not significant. Our population of dunkers in real life is very close to what we would expect if the population is in Hardy-Weinberg equilibrium. Now, what's that mean? First of all, to be in Hardy-Weinberg, the population has to be large. We'll get later to a more rigorous definition of what it means to be large here, but 3,500 dunkers is pretty large. Is there natural selection going on? Well, as I've said, your Mike November blood group has no known clinical significance. You're not significantly likelier to die of anything in particular if you have one blood type as opposed to the other. So there's probably no natural selection going on. This seems to be a neutral trait. Is there mutation going on? There always is, but mutation rates in the real world are low enough that by themselves, they don't push a population away from Hardy-Weinberg equilibrium, certainly not in any short length of time, and we can usually ignore that. So mutation rates are so low that it's not by itself, mutation's not having a big effect. Is it random mating? Well, as far as I know, the dunkers are not going out and selecting mates based on their blood types. I guess you could, but I've never heard of that. Dunkers would not have known about these blood types until the rise of modern medicine. So for over 2 centuries, the dunkers have been doing their thing in complete ignorance of what blood types they even have. So we can probably say that mating is random with respect to their Mike November blood type. And then the last, immigration or emigration, that's a potentially thorny one, but because humans do move around and there are dunkers that leave and there's people coming in, but not that many, certainly not that many back in 1950, because the dunkers' religious beliefs and their relatively isolated location in a rather hilly area of South Pennsylvania probably means that they don't mingle a lot. Now it might be different, but certainly in 1950, if you were born a dunker, you were likely to stay in the dunker community. I guess it's possible that you might leave, but there weren't a lot of outsiders coming in wanting to join the church and become dunkers. I mean, I assume they'd let you if you asked really nicely, but it didn't happen very often. So with this population, there's not much migration in or out. And as we've said, mutation's not strong enough to push a population off of Hardy-Weinberg by itself. The population's relatively large. There is no known natural selection, and mating is random with respect to blood type. So here we would expect that our population should be in Hardy-Weinberg equilibrium. And in fact, it's pretty close to being in Hardy-Weinberg equilibrium. So there. Now for part C, let me go back to the problem set. There it is. For part C, it points out that in Germany and in the Eastern US, about 30% of the population has type Mike blood, 50% is heterozygous, and 20% has type November. They are different for the dunkers, where type Mike is more common and type November is noticeably less common. There's several reasons why those allele frequencies could vary. One of them is the fact that in a small population, you get random deviations from Hardy-Weinberg called genetic drift, which we'll look at more rigorously later, probably next Wednesday. Another possibility is something that we call the founder effect. And in the founder effect, what happens is when you have a small group of individuals founding a new population, like a small number of dunkers leaving Germany and settling down in Pennsylvania, what very often happens is that one of the founders will happen to have an allele that's otherwise very rare purely just by dumb luck. Or that founding population will just happen to have an unusually high or low allele frequency purely by the luck of the draw. So it could be that of the first dunkers that founded the dunker colony in Pennsylvania, purely by chance, happened to have a higher frequency of the Mike allele and a lower frequency of the November allele. There's no interesting reason for why that is. It just is one of those things that happens. So it's possible it's the founder effect. It could be genetic drift. And again, we will look at both of those in more detail coming up. All right, I want to work problem 1, and then I'm probably going to leave you for now. So problem 1, okay, problem 2 shows you one of the 2 basic ways you can set up a basic Hardy-Weinberg problem. In the case of the dunkers, you knew the frequencies of the genotypes. You were able to calculate the allele frequencies from those genotype frequencies. And then from the allele frequencies, you could calculate predicted genotype frequencies if the population is in Hardy-Weinberg. And then you could test whether the population looks like it is in Hardy-Weinberg or not. Problem 1 is a study of the genetics of a Native American tribe in central Arizona, the Hopi. Still there, by the way. Still, going strong, I suppose. And a couple of people studying them back in the 50s, Wolf and Ducapo, found an unusually high frequency of albinos. In about 6,000 Hopi, there were 26 albinos. That particular form of albinism happens to be controlled by a single gene with 2 alleles. Albinism is recessive, normal skin coloration is dominant. And part A, the reason why you cannot calculate the allele frequencies purely from that information should be obvious. It's because albinism is recessive. And so just by looking at the Hopi, you can't tell who is homozygous dominant and who's heterozygous. You can't tell who is a carrier and who is not. So in this case, we cannot directly calculate allele frequencies. We were able to do it with the dunkers because we could tell all of the genotypes apart. We knew who was homozygous and who was heterozygous. Here, we can't tell that just by looking. We might be able to get some data on it with methods of genetic testing, assuming the Hopi would agree, which they might not. They tend to keep to themselves about certain things. So what can we do? The way we solve problems like this is, instead of calculating genotype frequencies and testing whether the population is in Hardy-Weinberg, we can assume that the population is in Hardy-Weinberg and calculate estimated genotype frequencies from that. So it's kind of working the same problem the other way around. Let's go ahead and go to the whiteboard. And let's make that bigger. And I'm going to go ahead and clean off the whiteboard. Okay. All right, there's our whiteboard. Okay. All right, so we have the Hopi people, and in a study back in the 50s, there were about 6,000 Hopi, 26 were albino, and I'm just going to call that genotype little a. And that means, of course, there were 5,974 Hopi that were not albino. And those could have either the homozygous dominant genotype or the heterozygous genotype. Okay. And our problem is that we can't tell those two apart. Now, ideally, we would be able to work out who is homozygous and who is heterozygous by some kind of testing procedure. But if we can't do that, what can we conclude? Well, we can say, let's assume that the population is in Hardy-Weinberg. If that's the case, then the frequency of homozygous dominance, big A, is equal to the square of the frequency of the dominant allele. The frequency of heterozygous people is equal to 2 times the product of the separate allele frequencies, 2pq. And the frequency of the homozygous recessive allele, the frequency of the albinos, is equal to q squared. Okay, now what do we know? We know that the frequency of the homozygotes and the homozygous dominants and the heterozygotes, if we're in Hardy-Weinberg equilibrium, is going to be equal to 5,974 divided by 6,000. Whoops. That is p squared plus 2pq. The frequency of the homozygous dominants and the heterozygous is going to be 5,974 divided by 6,000. Now, we could substitute q with 1 minus p and turn this into a quadratic. Or we could do it the easy way and note that the frequency of albinos, if we're in Hardy-Weinberg, is q squared, and that is equal to 26 divided by 6,000. And that means that, okay, 26 divided by 6,000 is, okay, 26 divided by 6,000 is q squared equals 0.004333333333. It's a repeating decimal. That means q is equal to the square root of that. All right. So let me see here. Okay, which button is it? All right, the square root of, oh, that can't be right. Square root of 0.0043333333 is 0.0658. Okay. So what that's telling us is that 6% of the alleles in this population, well, 6.58% of the alleles in this population are albino alleles. And because P plus Q equal 1, that means that P is equal to 1 minus Q. So P is equal to 1 minus 0.0658, which is 0.93. Come on, Wagner. I'm going to round it and say it's 0.934. Okay, so there. So now we've got our estimates for P and Q if the population's in Hardy-Weinberg. Okay, what do we do with that? If we're in Hardy-Weinberg, then our expected frequency of homozygous dominant individuals is going to be 0.934 squared, which is going to be, I think, about 0.82. So 0.934 squared. Okay, I take that back. It's about 0.87. Okay, so that's about 5/6. So 87.2% of the Hopi population should be homozygous dominant. The frequency of heterozygotes now, if we're in Hardy-Weinberg, is going to be 2 times 0.934 times 0.06658. And that's equal to, drum roll please, 2 times 0.934 times 0.0658. And that is equal to 0.123. So about 12% of the Hopi population should be heterozygous if we're in Hardy-Weinberg equilibrium. And then the frequency of little a individuals, we actually already know that because we just calculated. It's 26 divided by 6,000. And that's equal to 0.004333. Okay, so there. If we're in Hardy-Weinberg, then these are the frequency of homozygous dominant and heterozygotes. In other words, this might not look like a high frequency of albinos, but if we're in Hardy-Weinberg, then about 1 in 8 Hopi are carriers of the albinism allele. That's the kind of thing that you might want to know if you're dealing with public health. And there we've solved problem 1. Although we might want to ask, are the Hopi really in Hardy-Weinberg? Is our assumption likely to be useful? Well, is it a large population? 6,000's pretty large. Is there natural selection going on? Here there might be, because the Hopi live in the desert, and albinos with the ability to make melanin severely curtailed, you would expect would have a much higher rate of skin cancer. Certainly a much higher rate of debilitating sunburn. So it's possible that our assumption doesn't hold up because there could be natural selection acting against albinos. which raises the question of why the frequency is so high. This is not what you would expect. Something we need to investigate. Okay, mutation rates, like I said, by themselves, mutation rates are very weak at pushing a population out of Hardy-Weinberg conditions. So in this case, I'm going to say, probably not. Immigration or emigration, the Hopi are, I mean, there are people that move out, but it's a fairly close-knit society. There's not a lot of people that have left and very few people moving in. I mean, I guess it can happen, but there aren't huge amounts of immigrants into Hopi land, and there's not great caravans of people leaving. So not a great deal of immigration or emigration among the Hopi, certainly not in the 1950s when the study was done. Now, that leaves, the last one is non-random mating. I hesitate to say this because I don't know Hopi culture all that well, and I don't like making authoritative pronouncements about people where I don't, where I don't know their society very well. I have read that among the Hopi, albinos are actually considered to have special spiritual power and are actually in some demand as mates. Meaning if you're an albino, you may not be able to participate fully in the life ways of the tribe because you're not going to want to walk around in a loincloth in the desert. But on the other hand, there may be lots of people that want to have your kids. And if that's the case, then we might have non-random mating countering the effects of natural selection. And I hasten to mention that that's just something I read a long time ago, and I could be completely wrong about that. Certainly to know more about what's going on, we would want to, learn more about Hopi culture as well as Hopi genetics. But if we assume for purposes of this problem that I'm right, then the population might be pushed out of Hardy-Weinberg, but pushed out in opposing directions. Selection would be making albinos less common, but non-random mating might be making them more common. And again, that's a matter that should be investigated further. I don't know enough to say anything definite, but I hope you've at least gotten a sense of how to work problems like this. All right, by the power vested in me by the state of Arkansas, this is probably about as much fun as you can tolerate for one day. And it's a little bit late to start a new problem. So I'm going to go ahead and stop the recording, stopping it now.